Welcome to another topic of statics. Today we are going to concentrate on three-dimensional force systems. The objective of today's lectures and the activities are listed here. Students will be able to solve 3D particle equilibrium problems. Again, we are going to concentrate on particle. We would be practicing with drawing a three-dimensional free body diagrams and applying the scalar equations based on vector equations of equilibrium. As such, the activities include reading quiz, applications, equations of equilibrium, which is of extreme importance, the concept questions, group problem solving, and attention quiz. So let's get started with the reading quiz. You can read this, we can read this together. The quiz that's given here, question number 1, particle P is in equilibrium with 5 forces acting on it in the 3D space. And how many scalar equations of equilibrium can be written for point P? It's a very conceptual question, and this type of questions would be great to be put on an online exam. The correct response is not A2, it is not C, it is not E, and it is not D, but rather it is B, 3. Second question, in 3D, when a particle is in equilibrium, which one of the following questions apply? Summation of forces in the xi plus summation of forces in the yj plus summation of forces in the zk would be 0. This is correct. B, summation of forces is equal to 0. That is also correct. C, summation of forces in the x is summation of forces in the y, summation of forces in the z set to 0. Remember, I keep using the word summation, which is represented by this sign, well-known sign of summation. D, all of the above, and none of the above. Well, knowing that A, B, and C can be correct, then the correct answer is all of the above, which is the choice D in this case. Let's start with some applications. This is an example of an electromagnet. It is used in junkyard processing facilities and in metal scrap facilities, and any type of facility that it can be used to remove large pieces of metal. And the weight of the electromagnet and its load is given, but we need to know the forces in the chain to see if it is a safe assembly. And how would you do this? Well, we would take a look at similar cases, and what we do, the first step is to draw the free body diagram, analyze the forces, and make sure that the load doesn't exceed the capacity of the members. The second application is a derrick. The shear leg derrick is to be designed to lift a maximum of 200 kilograms of fish. This is in metric systems. And if there are any offset distances on the force in the cable, what will be the effect of the offset distances on the force in the cable and derrick legs? Very simple but interesting problem, and they are very applied. Let's talk about the equations of equilibrium in 3 dimensions, or the equations of 3D equilibrium. When a particle is in equilibrium, the summation of the forces acting on that particle is 0. So if when we are dealing in three-dimensional with a particle in 3D, the vector sum of all forces acting on it must be zero. It's shown here as summation of forces set to zero. Okay. So remember that when we have x, y, z, if we have a three-dimensional Cartesian coordinate system, then we are going to express our forces in terms of the unit vector I, j, k. In this case, the summation of forces in the x direction multiplied by I plus summation of forces of y, j plus summation of forces in z, k is zero. That means every time we have forces in the x direction, all of the components in the x direction of the three-dimensional force must have the scalar I or multiplied by a unit vector I. If they're acting in the y direction, it is multiplied by a unit vector j, and for k, that is acting in the z directions. So this vector equation will be satisfied only when the summation of forces in x, y, and z are zero. These equations are the three scalar equations of equilibrium in three-dimensional for any point in space that is in static equilibrium. Let's take a look at an example. The four forces and the geometry of the assembly is shown. What in this case, the particle O is placed at the origin of an XYZ system. As you can see, the XYZ coordinate system is shown as such, and that the positive direction is in the direction of X, Y, and Z as shown. The system may or may not be in equilibrium. We don't know about that. We would like to find a force F5 required to keep particle O in equilibrium. So what's the plan in this case? Think about it for a minute. The plan is, first we would like to draw the free body diagram of particle O. We're going to write the unknown forces, scalar in terms of IJK, and that's for F5 Newton. And we are going to write F1, F2, F3, F4, and F5 in Cartesian vector form. And we apply the three equilibrium equations to solve for three unknown F sub y, F sub x, and F sub z. So let's continue with that example to see how we can calculate F sub 1, which I often call F1 without using the sub, but you guys know that I mean F sub 1. So F sub 1 in this case shown as you can see, F sub 1 is in the YZ plane. In that plane there is no X component, only J and K components. The ratio of the components is shown here. The Z component must be 300 multiplied by 4/5, and the K component, which is in the Z direction, must be 3/5 of 300. So that would be F1. We do the multiplication, and this would be the force for F1 that's shown here in this form. F2 for force F2 or F sub 2. It is 600 Newton, and it is explicitly applied in the X direction, except in the negative X direction. So the force F2 must be minus 600 I Newton. Remember, the plus and minus signs are extremely important in this case. F sub 3, and force F sub 3 is acting in the negative direction of Z, in the negative Z direction, and it is minus 900 K. And remember, when the force is acting in the, for example, x direction, there will be no j and k component. If it's acting in the z direction, there will be no I and j component, and so on. For f sub 4 or f4, this is the scalar form. This is the absolute value, the summation of the sum of the squares. The square root of sum of the squares is shown here in order to calculate the magnitude. Before we do that, we are going to express it in terms of I, j, k terms. F4, let's take a look at the figure. As you can see, this is the end of the arrow, and as you can see, this is in a space. It's not just in one plane. The way it is shown by the given distances, 3 meter, 4 meter, and 6 meter. The 3 meter, the direction of the I is in positive, so it's 3I. J is in negative direction of Y, so that's minus 4J and plus 6K. Again, this is in order to calculate the magnitude of F4. We take the square root of some of the squares in the x and y and t direction. So 3 squared plus 4 squared plus 6 squared, we take the square root of the summation of those 3 squared. Then we would have F4 as 76.8I minus 102.4J plus 153.6K. And F5 would be F sub xi minus F sub yj plus F sub zk newton. That is for the unknown force. The direction of it is shown. We just need to follow the correct sign convention. It's in the positive x direction, it's in the negative y direction, and it's in positive z direction. As such, it is shown the way you see it down here. So what do we do from here? We take all the components with I, we take all the components with J, we take all the components with K, and we add them up and we set them to 0. For example, and let's take a look at all the forces with the I component. There is no I component in F sub 1. There is I component in F2, so we take this component minus 600, and there is also a 76.8. This is another. I'm going to pretty much put a circle around these. So we're going to take this component of the I. We're going to also look through other equations to see which one has I component. We take 76.8 that I'm encircling here, and F sub x also is an I term. So we take these 3 that are encircled, minus 600 plus 76.8 plus F sub x, we set that to 0 as shown here. So 76.8 minus 600 plus F sub x, set that to 0. We solve for F sub x, and from here F sub x would be 523.2 Newton. Make sure you guys grab a calculator and go through these calculations as I am discussing it here. Let me go back and take a look at the J components. Now on the second step, I'm going to take the J components. In this case, there is a 200J. I'm going to try to show this in a rather rectangle, 240J here. And there is no J component for F sub 2, no J component for F sub 3. There is also another J component. Again, I'm showing this in a semi-rectangle type of a shape, minus 102.4, and there is a Y component here. I'm also putting the sign inside the rectangle. So what we need to do for the second step is it is going to be 240 minus 102.4 minus F sub Y. Set that to 0, and that is how it is going to be. And after solving that, F sub Y would be minus 173.6. Again, grab a calculator and go through these calculations as I am go overing them here. For the z component, let me go back here. I'm going to just use underlining it on top. I'm going to put a double line on top of that to show the k component. So there's a 180k component for F1, F2 nothing, F3 there's another one which is 900k, negative 900k, and there's also 153.6 here, okay, and there's also a f sub z. So we add these four terms together, 180 minus 900 plus 1, and so on. We're solving it for f sub z, and that will be the answer for f sub z. So f sub 5 would be 523i minus 138j plus 566k Newton. We can use this vector, this force vector, and you can also determine the forces, magnitudes, and coordinate directions like we did previously in previous lectures as needed. So I'm not going to go over that here. So let me go over example 2. Example 2, given is a 600 Newton load that is supported by 3 cords with the geometry as shown, and they are point A is connected at 3 points C, D, and B to 3 different points in space. They are shown as such, and we would like to determine the tension in chords AB, AC, and AD to go ahead later and design them accordingly. So AD, AC, and AB is given. The angle of AB and y direction is also given. The y coordinate is also given. AB is in the XY plane. AC is in the negative X direction, and AD is in space. The D is at the end of AD is in space, having I, J, and K components. So our plan is to draw a free body diagram of point A. We let the unknowns to be for F sub B, F sub C, and F sub D. We're going to represent each force in Cartesian vector form, and it would apply equilibrium equations to solve for the 3 unknowns. Here's a free body diagram at A, F sub BD, F sub B, F sub C, and F sub D is shown. 600 Newton is acting downward. That is also shown. Distances and the angles are also shown. So first, in order to express F sub B in Cartesian coordinate systems in scalar form, F sub B is F sub B, sine of 30 degrees I plus cosine of 33 J's, 30 degrees J Newton. As such, sine of 30 degrees is half, so it's going to be half of F sub B plus cosine of 30 degrees would be 0.866 F sub B, and this would be F sub B. F sub C, again, if you look at the F sub C here, it is in the negative direction of X, so that would be minus F sub C I Newton. Then F sub D, it is pointing to the space, to a point in space. F sub D is R sub AD divided by the magnitude of AD. Remember, for the magnitude of AD, first you would calculate the I, J, and K multiplication factor, and then we would square those, and we would take the square root of the sum of the squares of those quantities. So 1i minus 2j plus 2k, 1 square, 2 square, 2 square, take to the half again, and that would give us f sub d the way is presented here. y1i because it is 1 meter in the x direction, and it is actually minus 2j because it's in the negative z space. It's in the z x space for that case, but it is shown as negative plus 2k and plus 2k because it is 2k in the positive direction of z. As such, this would be the equation for f sub d in newtons. And now we are going to equate the respective I, j, and k components to 0, as I just discussed for the previous problem. For the I components here, we have for f sub b, this is 0.5 f sub b. This is the I component, f sub c minus f sub c, f sub d, the y component, the x component, the I component, which is the x component, also shown here. So we just simply add these up. There are three unknowns here: f sub b, f sub c, and f sub d. Set that equation to 0. We repeat the same procedure, except this time we use the j components for the y and z components for z. There's also two components here, f sub b and f sub d. The good news is one of the unknowns could be solved easily using the summation of forces in the z, setting that to 0. And from here, we can calculate f sub d first. Okay, f sub d would be 900 Newton from this equation. So we solve this first. Then, knowing f sub d, we would solve this equation secondly. So that's the second equation we solve. And then, after knowing f sub d and f sub b, this is the third equation we solve for. Okay, so first we will calculate f sub d. So this is number 1. Then we are going to calculate f sub d. This is the second one. And thirdly, we are calculating f sub c. There are also other methods that can be used to solve that. So let's take a look at a concept quiz. So if a particle has 3D forces acting on it and is in static equilibrium, the components of the resultant force, summation of force in the x direction, summation of force in y, and summation of forces in the z, which one of these 4 choices is correct for the components of the resultant force? Let's think about it for a minute. A, have to sum to 0. B, have to equal 0. C, have to be positive. D, have to be negative. Right away, you should be able to tell that this is not the answer, this is not the answer. Between choices of A and B, remember, it is in static equilibrium, and this is for a particle that has 3D forces acting on it, so it cannot be this either. And the correct answer that's shown here is actually B, that I am encircled. Let's do another problem. It's what we call a group problem. Let's solve that group problem, and then we would have an attention quiz and wrap our session up. So for this particular problem, a 3,500 pound motor and plate as shown are in equilibrium and supported by 3 cables, and distance d is 4. Okay, d is 4 feet, the way it is shown here actually. Okay, so let's find the magnitude of the tension in each of the cables. Okay, so we would like to draw the free body diagram first. We would let the unknown forces magnitude to be f sub b, c, and d. As such, we would represent each force in Cartesian vector form, and finally we would apply equilibrium equations to solve for the 3 unknowns. Okay, so I hope you're all in the same page as you guys are with me. So let's take a look at the setup of the problem, the free body diagram of point A. This is a little more difficult to digest, but it is not as bad as many other problems can be. Remember, we are engineers, we solve problems. So we should not be afraid of any problems, no matter how complex it will be or it is. So W is shown acting in the Z direction. We put X, Y, Z as such. One of the most important questions that I get sometimes is, how do you know where to put X, Y, Z? Well, we do our best to optimize the problem. Fortunately, in this case, X, Y, and Z is given. But regardless of the X, Y, Z components, because we apply them to all of the forces, the final answer, regardless of the orientation, it should be the same. So F is 3,500 pounds, shown here upward. And the other components, F sub B is shown, F sub C is shown, and F sub D is also shown. So we calculate, we replace F by W here. We show that as W, weight or load of the unit. It is 3,500 pounds. It is acting on the positive direction of the Z-axis, so it's going to have a K component associated with that. F sub B, F sub C, and F sub D. We use what we did previously. We take the IJK form, and we divide it by the magnitude of each of them separately. In this case, again, we skipped the square root of some of the squares by not showing them, but check this out. Make sure these numbers are correct. For example, in the case of a 10.4 in this case, a 10.4 would be the square root of sum of the squares of 3, so 3 squared, plus 10 squared. So the square root of 109 would be 10.4. And the rest is the same thing, again, depending on the I, J, and K component, and they are shown as such. So if the particle A is in equilibrium, then the summation of forces must be in equilibrium. That is static equilibrium. That is for every particle in the world that is in a static equilibrium. This law cannot be violated. If this law is being violated, the object or the particle is not in static equilibrium anymore, and it is going to be dynamic. So we equate the respective I, J, and K components to 0. And the same way that we did with the previous two problems, we are going to apply the 3 scalar equations of equilibrium. Summation of forces in the X, we set that to 0. Summation of forces in the Y, we set that to 0. Summation of forces in the Z, we set that also to 0. We solve for the 3 unknowns. Okay, right? How many unknowns we have? F sub B and D. F sub B. We have 3 unknowns here. We have 3 equations. The 3 unknowns. We would solve for the 3 unknowns. How do I solve for that? There are many ways we can solve for that. You can use a matrix, and after setting up the matrix, you can use Gauss elimination to find the answer. The other method that can be done is first, let's find, for example, 4 divided by 11.2, 4 divided by 10.8. Let's simplify the equation. Then from here, for example, we can express F sub B in terms of F sub D, right? Then we are going to bring it down here and also express F sub D here in terms of F sub B. So here in this equation, everything would be expressed in terms of F sub B and f sub c if I do that. Then down here, I'm going to do the same thing. Express everything in terms of f sub b and f sub c. Then I can having two equations, two unknowns. I can solve for that. I can back substitute to the other equation, and then back substitute to the other equation and solve it. You can also use your programmable calculators. You can also use Excel. You can also use many of the softwares that are available out there that can do this calculation for you. So the first question that comes to your mind is, oh my God, am I going to solve that during an exam? You may not, most likely not, but you need to know how to solve those equations, because even though you are not going to be asked to solve that equation, just for example, you still need to know how to solve it. So you may get questions that ask you, how do you solve that kind of an equation? I know it's your math, and some of you guys may be very good at it, and my discussion here is really redundant, but I want to make sure that you guys know how to solve a quadratic equation, so we can solve and address such a problem during your homework and so on. Okay? Very good. Let's do an attention quiz. Four forces act at point A, and point A is in equilibrium. Select the correct force vector P. Okay, so we have these four forces, F sub 1, F sub 2, F sub 3. Again, P is included. So that's the fourth force acting at point A. Point A is in static equilibrium. Select the correct force vector P. Let's take a look at this to see what we can do here. Okay, so this is I, J, K components of each of them. So we are going to only see what's the correct force vector for P. Let's examine P. P is can be either in an X, Y, Z space, or the way it's shown here, it could also be in X and Z space, but we cannot really determine that, can we? The good news is that F sub 1 is along X, and F sub 2 is along Y, and F sub 3 is along Z. So if we can have that, if we set that using the equation of equilibrium, and we apply that, as you can see, F sub 1 must be a positive 20p, because P is also positive. See the I component of F sub 1 and P, and whatever that is, we should have some kind of a positive result. As you can see, we don't have those. The F2, force F2 doesn't have any I component. Force F3 doesn't have any I component. So the components of I must be positive. We don't have any of those here. So right away, just because of that fact, this is out, and this is also out, right? What about the J component? So let's say we're only left with two more answers, right? So these two are out, right? Both A and B is out. So we end up with two more, C and D. C, 20I minus 10J minus 10K, excuse me. Let's say that the I component can be positive. You can have, for the sake of argument, plus 20I. Can we have any negative J component? Again, I'm examining the sign to see if the sign gives me any kind of a clue as to what the answer would be. So in the J component, let's see, the J component, can it be negative or positive? For F sub 1, there is no J component. The only J component we have is, it could be for P, and also for the 10. So P, if F sub 2 is 10 pounds, that's in the J. P, can P have any J component? Maybe, maybe not. Could it be negative? No, it cannot be negative. It must be positive. So this is also out of the question. The answer would be none of the above. That is the correct answer for this particular problem. I can go crazy a little bit with it and just say that is the correct answer here. D, none of the above. That brings me to the end of the lecture. Let learning continue. As always, if you have questions, you know how to find the answer or how to contact me. Thank you.